I'm in the definite minority in the classroom.
Choice to take it, not take, we know the choice that we don't always want to take, right?
Real quick,
After suffering.
one thing about chapter 8, I want to get off my chest here real quick. I was trying to go on the fly, come up with a different way to explain things. I had mentioned something about, so this is a really interesting idea. What's the only number I could put? So come back out of matrices. Come back to just normal. Like if it's 7x equals 14, x is 2. It's amazing. Because I can invert 7. I can multiply both sides by 1/7. Right? So of course, what's the only number I can put here that I wouldn't be able to do that? 0. Because 0 is non-invertible. Right? If I try to invert it, it freaks out. Okay. Becomes undefined, goes infinity, whatever way you want to look at it. But when I step it up to another dimension of things, the idea of 0 becomes a little more generalized. It's really interesting. So something have a 0 determinant means it has qualities like 0 in a few different situations, which is really freaky. So if A is invertible, then I can just operate on both sides by A inverse, and I get an answer for x. So remember, the thing we were working with, and to be invertible, the determinant of A cannot be 0. If the determinant of A is 0, then it's not invertible. So you could find an inverse matrix. That's actually something you should have done in pre-calculus, finding inverse matrices. Again, I'm sorry if that didn't happen for you. Now, does this semi make sense? It is kind of related to the inverse. Over there, though, it's reciprocal. It's involving division. There is no such thing as matrix division, really. Although that might just be a semantic thing, but it really is. There's no such thing. I operate with the inverse matrix. So it's a little bit different. So what we are working with was this. K is a matrix. It's a solution matrix. It's got the coefficients, the constants that I need. I was trying to look at it in an easier way, but then I was not writing things correctly, and it just kind of blew up. So the same idea here. I don't want this to be just zeros. I want to know what values, are beyond the trivial solution. So in order for this is AX equals 0. If this was invertible, I could just operate on both sides and I would get K equals 0. So I need this to not be invertible. I need the determinant of this to be 0 so that it's not invertible. So therefore I get non-zero answers for K, if there are any. Right? That's that one key step. And the way I was writing it threw me off as to what the connection was. Because I was trying to figure out on the fly a way to explain it without it being too matrixy. But the whole chapter 8 is all about matrix ways of solving things. So there was really no way to do that. So that's why this key step, that's the key step. That's why that key step happens. And then the actual nuts and bolts thing you do is relatively easy. As long as and if you understand that step, that's why it becomes so easy. Okay, that's enough about chapter 8. Does everybody have a copy of the practice that needs one? If you didn't print one out, you can have a hard copy. Okay. So I got the answer key. I think, which one was it? Number 6. I don't know if you tried number 6. I don't know if I meant to make it minus 20. It would have not been quite as, well, I don't think it was so evil, but you'd have to do a little extra stuff with number 6 since it is plus 20, because then it's not factorable, for example. Right. So what I want to definitely focus on, even if nobody has a question about it, is some problems where you have to complete the square to see where it goes from there. Because I don't think we've done like a lot of those. And that's one where that would happen. Where else does it happen? Oh, well, 7C, it just happens very directly. So maybe that's a good place to start. If anybody have other things you want to look at, or is that okay? Yes.
If you can explain more about ordinary points and singular points, I think in lecture you kind of just handed out the worksheet.
Yeah, so a singular point is where, so for example, if I look at this guy, the very first one, and technically I need to look at P of x and Q of x, but if I'm talking about polynomial coefficients, I can actually leave it like this. If the first guy, whenever this is 0, when it divide to create P of x and Q of x, obviously they're going to have a problem anywhere this is 0. So a singular point for this DE would be x equal to 1. So is x equal to 0 a singular point? No. So it doesn't have it's not undefined there, and this if I do divide, this function is it analytic at 0, meaning is there a Taylor series that I could create for this? Yeah, I can find derivatives, I can do all that stuff, so it's analytic at 0, so it's fine. In fact, I could have asked you to solve this thing. I don't know if you guys remember, we've done some of these with series solutions where you have this, so you have to do x times the series thing minus the series thing. We've done that before, so one of them gets a power boost and the other one doesn't. Okay, anyway, I didn't ask you to do that one, but so what's really, how many of those in number 1 have 0 as a singular point? Just one of them. Which one? B. Right, if I divide by 2x to get the y double prime, the highest order thing by itself, to get it into standard form, I end up with something over 2x, so therefore 0, it wouldn't be analytic at 0. Okay, I like it. So that's the only one that's got a problem. The rest of them are fine. The rest of them are perfectly fine. Notice how D and E are almost the same thing, really. D is sine x analytic at x equal to 0. Yes, sine x has a power series, has a Maclaurin series, right? Where x equals 0. How about an x squared? Its power series is x squared. So yes, it's analytic. It's got a power series centered at 0. I like it. Okay. So one, they're all ordinary except for part B. So there was that, I think on there I also said, if you're dealing with polynomial coefficients, that's the quick way to look at it is, where's the first, the guy in front of any coefficient of the highest order term, wherever that thing is 0, is where this is going to have trouble. So, if I have this here, where's this guy got singular points? 3 and negative 3. I like it. Cool. You could have complex singular points, but we don't really study complex solutions to DEs too much, besides rewriting that one complex answer we got in terms of cosine and sine, which is sort of not directly tackling that issue. Yeah, but this is not a complex plane course. You don't want that until later. Okay, does that make more sense? Okay. And that section 6.3 classified singular points a little bit more. I have no problem skipping 6.3 because it's just such a convoluted kind of approach. Nothing wrong with it, you have to do it sometimes, but they skip a lot of the idea about where things come from, which really irks me. So, like last semester, I think I did something and I showed people where pieces of it came from, and they glossed over, so I don't think I'll do that again, because it's just a long, involved thing. And you're all like, that's what this whole semester's been, Joe. All right. So where else do we want to go? I was going to eventually do 7C. Let's do it. 7C. Sometimes I make my L all nifty, and sometimes I don't. So, I mean, what prompts me to do something weird with the bottom here? I mean, if this 5 wasn't there, what would I do? Partial fractions, right? Because I can factor the bottom, no worries. That, yeah, I could factor it. I could. I don't want to. It's gross. So we don't, right? So take a second and see. Can you guys? Well, this one's not too bad. There's a few different ways you could do this, but one has to go here. No. What are the steps? Half of this dude squared. Yeah, 11. And why is that true? Because if I do this, I get x squared plus 14x plus 49. That square is that, and then cut in half is that. Right? So if I know this number, I cut it in half to figure out that number, and I square it to figure out that number. So I cut it in half, I get 1. So that's going to be how this is going to factor. And then I put square the 1, I get 1. I had 5 here, so now I've got what over here? 4. All right. And then how do I go from here? Well, this is what kind of thing is happening here.
Translation is a...
Yeah, so very often, yes.
What happened? Why'd your 5 go to 4?
Well, 5 went to 1 plus 4.
Oh, okay. I see.
That 1 is needed by this guy.
Yeah.
So there's a 4 on it. What you can do also is, you could say, leave some room, put the plus 5. This needs a plus 1, so I better minus 1, so overall I didn't do anything.
Okay.
And my poor students, they've never seen freaking Indiana Jones. Where he, does this, and it's like, he didn't do it correctly, he didn't balance his equation correctly, the boulder came down. Death, he escaped barely. Math will save you. And so, I don't know what way you guys have chosen to do this. I tried to not give a specific way to go from here. I sort of gave an idea of the way I do it. I kind of go, I do this. Knowing that my answer is going to have an e to the negative t. And now I can just focus on that. And the book's got a weird way where he has s goes to whatever, if you like that way. So this way I can just focus on the form. To be really, really honest, I don't do this step. Really. But here you can focus on this. What is this going to be related to?
Sine.
Yeah, sine, because the top doesn't have s. That would be cosine, the little asshole took the s. And of course, what's supposed to be up here?
2.
2. Yeah, because this will be k squared, right? So then what do you have to put out front?
1/2.
1/2, so you can put a 2 there. So this will be 1/2
Because it's inverse, that's why.
sine. No? Sine 2t. Okay, so now I'm open to suggestions. We can look at number 6 because I didn't finish it on here. Where are you? There you are. Oh yeah, I got that far. I was like, screw this, we'll do it in class. If you want to.
Which one?
Number 6
Looks fun.
looks very much fun.
You could play with big one.
Yeah, you guys try to get number 6 started if you haven't done that one yet. Then I'll catch up to you.
Yeah, right on the bottom. Come at the bottom.
How'd you get from the second to the last one? The last one?
Finger.
Oh, all right, so what I did from here to here
Yeah.
was I wrote this down. I knew that was gonna become that, and then I could just focus on the form. I already wrote down the part that was the translation. And then I can just see what the real form was for the rest of it.
Okay.
I lock it. So really, this becomes this. Right, and then you can just focus on what this is gonna be. I lock it. Laplacian of little y becomes what?
Big S, Y of S.
Big S, y of s. Let's get out of
S.
here.
Big
S,
S, Y
y,
of S.
s,
Y of 0.
y 0. Good. And then multiply this by s minus
Y prime
y
of S.
prime. So then, triple prime, and we multiply this whole thing by s, minus y double prime is 0. So a very nice iterative way to get successive things. And I just got to throw that into here. So y double prime becomes this business. And then I got minus 8 this, so minus 8. So minus 8 times this, and then I've got plus 20 this. Gather. Equals, and what's the Laplacian of t e to the t? Laplace of t is
1 over S squared.
1 over s squared, and e to the t is just a,
Translation.
yeah, why am I doing that? Yeah. So it'll be
S minus 1.
coolness. Now, I think all these are 0, right? So y is 0, 0, y prime is 0, 0. Yes. So then you just end up, is this good so far? You guys cool with this? And real quick word. I don't know if you've noticed this yet. I don't know if enough people have told you about this stuff, but if you look into the history of almost anything we do, it either had its beginnings in astronomy or in gaming theory, right? Because we either sat around looking at stars or we tried to cheat people out of money. So we tried to figure out the optimal way. It may not cheat, but just have an unfair advantage over people that didn't think about such things. So then we have s squared minus 8s
Plus
plus
20.
20 s, and that's the thing to look for, is that's the look of the original problem, right? That should kind of come out. Equals 1 over s minus 1 squared, so it can get 1 over s minus 1 squared, s squared minus 8s plus 20. Poor little 1 being divided by so much shit. It's like, oh man. So you know that these coefficients, these A, B, C, whatever, are going to be a little gross. Got a lot going on just underneath the 1. Right, so this problem was kind of ugly. So what do I do next?
Partial fraction.
Partial fractions. And I'll warn you right now, you get stuff over 169 and stuff like that. Yeah.
Tasty.
So you get, so let's see.
So I focus on the partial fractions.
Where can I do this? What's it going to look like, the form of the answer? It'll be
A over S minus one
a over s minus 1,
plus B over S minus one.
b over s
squared
minus 1 squared.
Plus C over S plus 10.
Carol?
CS plus D.
Yes. cs plus d over s squared minus 8s plus 20. So this isn't truly quadratic in the terms of what partial fractions looks like. This is a repeated linear. So the tops will be 1 degree below linear, constant. This is truly quadratic. So and it's irreducible in terms of, whole numbers, integers. So the top will be 1 degree below quadratic, which is linear. That's how partial fractions work. Here. So I get 1 equals a times s minus 1 times s squared minus 8s plus 20 plus b times s squared minus 8s plus 20 plus cs, cs plus d times s minus 1 squared. Hopefully right now, whatever they already have, they pick up the other shit. You have to actually multiply by the s. And now, what would I do?
Plug in values for S.
Yes, as much as I can, and the only one I really can use is
S
one.
equals 1.
Now, to be honest, you can use more than just one and kind of generalize it. But then you just end up with systems of equations anyway. You might as well just equate coefficients. So if I let s equal 1, all that's left alive will be this b term, and all you get on this side, no matter what s is 1. So I get 1 equals b times 1 minus 8 is negative 7 plus 20 is 13. So I get 1 equals 13b. b is 1 over 13. And now you just got to make systems of equations for the rest of them. How many ways is there to get s cubed? I mean, now it's really up to you. I mean, there's so many places when you get higher in math that certain teachers let you have some room to make your own approach. Personally, what I would do very next thing is s cubed. What ways is there to make s cubed?
C will be S cubed.
Yeah, cs cubed
A.
and as cubed.
Mhm.
So I know that a plus c equals 0. Now, I got to bring the rest of this in here somehow. So what about, I'm going to probably have to break down and do more than that. What about constants? Negative 20a
B.
plus 20b.
D.
Yeah. Plus d. That's going to equal
1.
1. That's the constants. I love it. So I know b. I still need one more connection. And again, if you don't like this approach, if you want something a little more systematic, then just multiply shit out, get your coefficients of your like terms together, make a big old system of equations. Nothing wrong with that at all. Let's see, what else can we do here? Oh, this is gross. So I can look at, this guy is the grossest piece, really. It's got, this is bad too, shit. I'm going to have to just break down and multiply some stuff out and get like my S terms or something, right? There's really not much else I could do.
Why can't you use quadratic formula to break down the S squared minus 8 and find the S and plug it back in and solve for it?
You totally could.
To do the long way.
You totally could. All right, now watch. So what you're saying is get the solutions for this, because then to make it 0, and then that would make this 0 and this 0, and then you can just deal with this. But then you've got 2 unknowns here.
Yeah.
You know what I'm saying?
Yeah.
But still, that would work. Of course it has to work. Because I used s equals 1. You should be able to use s equal to whatever the shit makes this 0. Right? All day long. I don't know if you really want to.
No.
All right.
I just suggest an idea.
No, I'm with you. So we're just going to have to suffer through this. So I get s cubed minus s squared minus 8, so minus 9s squared plus 8 plus 20, so plus 28s minus 20. You guys can double check me on that thing. And then here, this is pretty simple to see. And then this guy, this is gross. If I do this, I get CS times this will be CS cubed. This will be minus 2s, so minus 2, well, it'll be s to the fourth one, and s to the fourth. Ooh, this is gross. All right, you ready? This will be s squared. Oh, yeah, so that's CS cubed. This will be minus 2s times that, so that'll be minus 2CS squared. Just look at the C. Plus CS. Plus ds squared minus 2ds plus d. All right, that's pretty gross. So then let's see. Then we can make one more. Let's double check our what we got here. Negative 20a plus 20b plus d equals 1. That checks. Right, that's your constant terms. Yes?
How do you know a plus c equals 0?
S cubes. There's no s cubed.
Oh, okay.
Yeah, S cubes are the highest power and the lowest power are the easiest things to get. That's why I got those first thing. And then I just didn't have enough. I had to get one more thing. So now I can look at my s squares or my s's. Doesn't really matter. So if I look at my s's, I got 28a minus 8b. You guys see what I'm doing? Getting all my s terms. Plus c minus 2d. Equals 0, because there's no s terms. So what I can do now is I know that b is 1/13. I know that a is negative c. Right? So let's see. A is negative c, so that this becomes, I don't know if you guys, how much more s you want to do. So this becomes negative 27c, right? A is negative c, is that cool? This becomes negative 28c plus c, so negative 27c. Is that the way I want to go with that? Maybe, we'll see.
Minus.
No, I'll tell you what, I want to go the A way. You guys see what, because there's an A here? So if I do c is negative a, I get 27a minus 8/13 minus 2d equals 0. And this one is negative 20a plus 20/13 plus d equals 1. My God. So then from there, now do you start to see why I think I meant to make it a minus 20? Yeah. I don't think I meant to make it this way. But still, I mean, this is doable, but maybe not in an hour and 15 minutes. As one part of a test. But you guys see where I'm going with this, right?
Yes.
You guys see how I checked myself. I started having C's in this, but there's no C's here. So how could that possibly help me? But there's A's. Okay, I want to make this A. Now between these two, I can kill the D's, for example, right? I can pull the numbers over. I can kill the D's. Okay, that's enough of that one, I think. When I go, let me focus on this. When I go to do the inverse Laplace, I'm going to have something with. I want to do the inverse Laplace of. Just going to make something up here. 13 over s squared plus 8s. Nope, sorry. Minus 8s plus 20. How would I start to do this? Let me make this 13s. Yeah. Probably. That actually makes it easier. That's all right.
16.
Yeah, so to complete the square, half of negative 8 is negative 4. So I already know how it's going to factor. The first step tells you how it's going to factor. And the next step tells you what you have to add. So I have to add 16. I've already got 20 there, so that means what's going to be out here.
Plus 4.
And now that wouldn't be that bad anymore, right? Me, I would say this is the inverse plus of 13s over s squared plus 4 times e to the 4t. And I can focus on that. That's going to be a what? Cosine. I love it. The 13 is that bother me. No. It's the sine that has to balance with the k on top, right? The cosine has an s on top. So this is just going to be 13 cosine of what?
4.
No?
2.
2. T. E to the 4t. It's kind of convention to put the e to the 4t out front. Because then we allow for 2t to not be in parentheses. Here it's kind of like, is this whole damn thing inside the cosine? Yeah.
Is it not negative 4t? Oh, okay.
That's the shift, right?
Yeah.
That's the shift on the s-axis. So it's got to be positive for it. I like it. It kind of sucks when there's multiple 4s. You're like, where's that coming?
Yeah, I was looking at that step right there.
I'm with you.
Sorry.
So somewhere in your future you would have this thing which is going to have a cs over this. It would be the same kind of thing. And this one would just be the sine piece. I like it. Okay, cool. If you really do enough of this and you compare it to what we've done before, it's kind of an alternate way to see why the pieces come together, like why sine and cosine come together. Because you're going to have this kind of thing over irreducible quadratic, which would come to sine and cosine. You got 2 pieces to it. It's crazy. All right. Anywhere else we want to focus on specifically?
Can we look at 2b?
Yeah. 2b involves... What do you think it's going to involve? I mean, normally if I have an x coefficient, I just multiply it in. No big deal. Because it's a single x term. Now, I have to do the same thing here, but I'm rewriting my y's in terms of power series, so I probably have to rewrite my sine x.
In terms of its power series?
So if I gave you a problem like this, I didn't make you memorize the power series stuff, so I'd give you a list of power series that you could choose from.
So you just multiply whatever that power series for sine x is
Yes.
in front of the...
Term by term, and you only have to do, if I remember, I'll be specific, but otherwise just go out to like, 4 terms, only a couple for each y1, y2. Do you see what I'm saying? I'll try to remember to be specific so you know how far to go out, how far is enough. Sometimes I have poor people that are like, C12, C13. And I'm like, no, you don't have that time. So let's see. It's really worthwhile. I mean, this is not something that takes forever. Let me talk about this real quick. So why does this happen the way it does? Let me focus on this for a second and relate it to something else. What's the derivative, of course, here?
C n
And
times n minus 1.
Now, I don't have to change this, but why do we? Because n equals 0 would lead to a 0. So why would you start at 0? But, and then y double prime is going to start at 2, because now n minus 1 is going to come down. All right, but there was a problem on the quiz that looked something like, I can't remember now. Doesn't matter. Just to make it more interesting. Sure. Now, real quick, see, this one is, if you wrote some terms out, what would it look like?
C0 plus
C1x plus C2x squared.
It's really useful to remember. That's all this means is this. And it's kind of like reassuring to see that every now and again. Because you get so wrapped up in this weird, oh, this is all new. No, it isn't old shit. So, I mean, in a weird way, what I'm about to say is true and also completely not true. But if I take the derivative of this, don't I lose a term? But I have an infinite number of terms, so I didn't really. But still, I lose that first term, and therefore I got one less term. So that's why I can start at 1 now. Because this thing started at a constant term, so when I take a derivative, but what does this thing start at? N equals 1, this will be 3c4 x to the 2 plus stuff. So one derivative, I'm going to have the same number of terms. I can't change my index because then I would actually lose a term, not a 0. That was what that last quiz problem was about. Really, the derivative should have been easy as shit. It's just power rule. The thing that I'm looking for was, do you realize you don't have to change that index? And then I realized some people might just luck into that and not even realize they sometimes should change it. But I'm like, oh well, that's good for them. Okay. That's pretty much always the same for these solutions of these using power series. So I don't know, it's pretty quick to get those. I don't know if anyone wants to memorize those. Now just throw those in. Now what's sine x? Anybody know? Sine x is approximately what for very small oscillations? Yeah, sine x is approximately x. So the very first term of sine x expansion is x. That's awesome.
Minus x cubed
Yep.
over 3 factorial.
Yeah, I was dumb.
Plus x to the 5th over 5 factorial.
Yeah.
Minus X and stuff.
And this will be times this guy. Let me take these away. We got what we need from these guys. Times this guy. Yeah. I should have just expanded him out like I already did, but I won't do that. Let me do that. Let's just rewrite. We already expanded it. We need it expanded a little bit. This is kind of nifty how this works. I can start looking at specific like terms here. So, well, first off, let's multiply this out. So let me just write. Let's just write some terms here. What do I get for n equals 2 here?
C2.
Yeah, 2 times so 2 c2 x to the 0, right? Plus. Yeah, 3 times 2, 6, C3, x, plus, yeah. So this is 1 times 2, 2 times 3, 3 times 4 is 12, C4, x squared. Let's just do one more for fun.
20.
Yeah, 4 times 5, right?
Yeah,
20, C5, x cubed.
This is
Da, da, da.
this is that last summation there.
This is this one, yeah, exactly. That is this.
Sorry.
The first few terms.
Looking down.
Like, and then, what do we get over here? And what you can do now is sort of like what I do when I foil anything out. You know, I hate that word foil, but you start thinking, how do I create, is there a way to create a constant term from this? No, because the lowest dude here is x. So everybody's going to have at least an x. So how many ways can I get something x? There's really just one way.
C0X.
If I multiply anything else, right? And that's the power of these series, because they just keep increasing in degree. So you know for sure how many ways there is to make so many lower degree stuff. You can see everything. So C0x is the only way to make an x term. And then how do I make an x squared term? How many ways is there?
Not
One.
1.
There's only one way. What's that one way?
C1X.
C1x times x, so C1x squared. How about x cubed?
Just multiple ways.
2 ways.
There's a couple ways, right?
Because C2 x squared times x.
Yes, I can do C2x squared times x, so it's C2 x cubed plus,
That term,
right?
yeah.
It's actually minus c0 over 3, I gathered 3, 6 x cubed. Dot, 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 right? So now I got, this is my only constant term, right? Equals 0. If I will equals 0. So I have c2 equals 0. I have 63
Plus C0.
plus C0. 63 plus C0 equals 0, because there's no terms. It's equal to 0. So all my like terms, coefficients, have to combine to be 0. You guys with me? This is actually that recursion step done one by one by one, right?
12C4 plus C1.
Yeah, so now look at my x squared terms, 12c4
Plus C1.
plus c1 equals 0. And then, let's see, I got x cubes, 20c5 plus c2 minus c0 over 6 has to be 0.
Well, we know C2.
Yes, sir.
So when you expanded that or foiled that, did you just go C naught times X?
And again, you do it in a very prescribed manner. I'm not actually going to just start distributing because that would, I had to write a lot of terms for myself. I go, okay, how can I get a constant? I can't because it's going to be x at least times stuff. So let go of the constant. How do I get x? How many ways is there to get an x? X times c naught. There's no other way. Because if I do this times something, right? But depending on what these are, maybe there are multiple ways. So that's why we only had one x term, no constant term. What about x squared? There's an x squared, but the lowest thing here is x. Oh shit, so the only way to get x squared is this guy's x times this guy's x. The only way to get an x squared term by multiplying terms between the two is this times this. There's no other way. There's x squared times, oh shit, there's no constant. If there was a 1 plus, then there's a couple ways to get x squared.
So you just need an X squared and X cubed.
Yeah, start with constant, x squared, and then x cubed is probably plenty enough to get an idea. And again, depending on the application, you can just go further out if you need to be more precise, right? If the actual values you're using are far away from 0, you need to be more precise. You need to go further out in the series. And then the cube, of course, one way is to take x times the x squared piece there, and to take the constant times the x cubed piece there. See, that's how to get x cubed. There's two ways. This has got an x. So if the other one's got an x squared term, there's a way to get x cubed. This has got an x cubed. If the other dude's got a constant term, there's another way to get
So you need to capture both of those ways.
You need to do all the ways to get that power. In fact, I don't know if you guys paid attention. When I do this, I don't write all this shit out. I go x cubed, and then how many ways? How do I make an x squared? This way and this way. And then combine them, right? It's the same idea here. It's a little more involved here, but it's the same exact idea. So I don't have to spend my life writing shit down that I don't need.
So
I'm going to
how
combine
you
it.
do x to the fourth then? Will you expand it more?
Yeah, I'd have to give myself a few more terms to get x to the fourth.
Okay, got it.
I like it.
You're like in a problem to find the fourth degree.
So to be safe, you should go a little further out than you might think you have to. Right? If there was a constant term here, there's another way to get x cubed.
Yeah.
Once you have to go further out, there could be like, well, this x times this x cubed, and this x squared times this x squared, and this x cubed times this, and there's a lot of ways, and you go a little insane. But for me, you don't have to go that far out. We're not measuring gravitational waves, so we don't have to be so precise. Now here, I see that C3 equals negative C0 over 6. Is that cool?
Yes.
That looks like something we're used to. I see that C4 equals negative C1 over 12. I see that what's C2?
0.
0. I see that C5 equals C0 over 120. Right? C5 is a decent distance out for our purposes. So then I end up with what I have so far. I got y equals C0 plus C1x plus C2x squared plus C3x cubed, C4 x to the fourth, C5 x to the fifth. I mean, that's a decent distance out for the solution. Right? The step that people very often forget is this is my answer. This is my answer. That's why figuring these out gives me the answer, because that's all I don't know. That's why I call those the DNA of the function, because every single function that has a Taylor series has a representation like this. The only difference between them then is the Cn, is the actual constant series, or sequence in that case. So you can do your y1, look at the C0s, y2, look at the C1s. I like it. Let me give you guys the answer key before I get too far. It comes in two parts. So I hand wrote each of these. I'm joking. Somebody actually thought that once when I copied the purple thing I used. These few parts. I love number 8 because 8 looks like it's going to be so difficult. But it ends up being really simple. I mean, imagine number 8 using undetermined coefficients. Right? What would you have to assume the form of the answer? For number 8, t cubed d to the 2t, you'd have to assume at cubed plus bt squared plus ct plus, oh my god. And the Laplace version just very quick. Well, you know, and that doesn't always happen. I'm hoping this looks alright. I was going to grade homework, so I don't have your homework done because I couldn't find the answer key from last semester, so I had to make this today very quickly, so sorry. Your homework did not get looked at. Let's see, if you- Why did I do that? Boy, I really made that one crazy. Oh, so there's an alternate way to do 3e. I chose to do it a very interesting way. earlier we talked, I got what they want from this one before. Yeah. What's the other way to do 3e? I chose to complete the square on the bottom, which makes it a minus k squared, which makes it a hyperbolic. What's the other way to do 3e? Well, the bottom you can...
Factor out s.
Is it supposed to be s cubed or s squared?
Oh, s cubed. Oh, I didn't even... Oh, man. All right, so let's do this one. Because I looked at it like s squared, so I did... That's wrong. That's amazing. Yeah, I totally looked at it like an s squared. All right, so let's do this one. Oh, this one's actually cool because it's going to come out with... All right, let's see what happens.
Factor out s.
Say again?
Factor out s.
Yes. All right, so now you can do 3 over s squared plus 4.
And now
Partial fractions.
Yep, so you get 3 over s squared plus 4 equals
3 over s. I mean, sorry, a over s.
a over s. I was like, wow.
Plus 1 over s plus 2.
Careful.
ds plus.
So it's truly quadratic. No, okay, I'll show you in a minute. And now, of course, so 3 equals a times the stuff it don't have, plus bs plus c times the thing it don't have. You guys keep going with that.